So, good afternoon, everyone. Maybe good morning for someone. First of all, I would like to wish you all a very successful and fulfilling academic year. I hope this year brings you new opportunities for growth, learning, and collaboration. I would like to take this opportunity as we take this first session, which also marks the 4th anniversary of this webinar, to express my gratitude to its original founder, the person who had the idea to create it, Professor Nabil Gmati. It is my pleasure to introduce our first speaker for this 5th year of this webinar, Dr. Khaydar Nurligareev, from the Laboratory of Interdisciplinary Research at the University of Burgundy, France. Dr. Nurligareev earned his PhD in 2022 from LEPN at the University Sorbonne Paris under the supervision of Professor Lionel Bournier and Thierry Montel. His research focuses in enumerative and analytic combinatorics, and he also has a strong interest in Teeling and lattice models. We are honored to have him with us today, and I am sure his insights will be both inspiring and thought-provoking. Without further ado, please join me in welcoming Dr. Khaydar Nurligareev. Today, the talk of our speaker has as title Asymptotics of Consecutive Patterns in Permutations and Matching. And please, Dr. Khaydar, you can start your talk.
So thank you very much for this introduction and for this opportunity to present my work today. It's a pleasure and an honor for me. And today I would like to present the work that I was doing with Celia Bian and Sergei Kirgizov, who is here now. And this work is partially continuing. So maybe there is something to add later, I mean, in upcoming months. So first of all, I would like to tell something about the structure of my today's talk. So there are two big parts. The first part concerns consecutive patterns in permutations. The second concerns consecutive patterns in matchings. And between them, I will tell you about some small piece which sounds interesting to me about self-overlapping permutations, which is kind of related to both these parts, but at the same time, which is a bit different and out of the way. And if I have enough time, I will show you some ideas of proof very shortly. So let's start with the first part, patterns in permutations. I guess the most knowing, the most familiar to people about patterns, it's what is first come to mind when you hear patterns. It's the following. So if you take a permutation, which is here is in square notation. So we take a square and we write dots, we write points in the positions, depending on the height. So if we take a permutation and we remove some columns, for example, here we remove columns number 1, 3, and 5. So what is rest? Here are the blue dots. So what is rest is called pattern. And we can see here blue dots represent a pattern 1, 3, 2. And this notion of patterns in permutation is the most knowing, that is something which is widely studied. A lot of studies about patterns avoiding and so on is known, but there are a lot of questions as well. In my talk, I'm going to concentrate to focus on more narrow, or I would like to say a more strict notion of patterns. So first, I would like to say that if we restrict our patterns to be consecutive, means that if we look in the second picture here, the entries, the positions of entries should be consecutive. So the positions are 2, 3, 4. And we as well remove all other columns. So as well, we have a pattern 1, 3, 2. So comparing to the first notion, the consecutive patterns, or which is called tight patterns, which is called by Bona, Miklos Bona. So here is the difference is that all positions should be consecutive. And in my talk, I'm going to go even further. Namely, I would like that the entries themselves should be consecutive, I mean the vertical positions should be consecutive as well. So this kind of patterns is referred as very tight patterns. And we say that a pattern very tightly occurs if there is a block like this that represents this pattern. So here it's also the pattern 1, 3, 2. And so in my talk, what I'm going to discuss, I'm going to discuss only very tight patterns. So let us first look at the enumeration of very tight patterns. It is done by other people, not by our team. But we are going to look how it works. So for very tight patterns, there are two different situations. Either these patterns cannot overlap, as in this example, the pattern 1, 2, 4, 3. If there are two patterns in one permutation, then these two patterns don't overlap for sure. And this case is easier, and its enumeration can be done with the inclusion-exclusion principle. At the same time, if patterns can overlap, as in this example for the pattern 2, 1, 3, 2, we can see the three patterns in the row that overlaps that overlap with each other. So in this situation, the enumeration is done with more tricky method, namely by the Goulden-Jackson cluster method. So let us see how it works. So for the first case, for the patterns that cannot overlap, we can see that what can be done. We can, in fact, exactly enumerate the number of permutations of a given size n with exactly k very tight occurrence of a given pattern. So the formula is here like this. This formula was found by Myers 20 years ago, even a bit more. And let us quickly look at this formula and understand how it works. So in the basis of this formula, it is the inclusion-exclusion principle. And we should write this formula from right to left. So we start from the last factor. It's the number of permutations of this size. And what we do in these permutations, we take I positions and replace these positions, replace these dots by blocks. So for example, here we have a permutation of size 1, 2, 3, 4, 5, 6, 7. We choose 3 positions and we replace them by this pattern. And if the obtaining permutation have no other patterns of this type, then it's exactly what is counted. If not, these two additional factors, as it works for every inclusion-exclusion principle, they guarantee that the resulting terms cancel out, and so the result will be correct. So that is the idea of this formula and of this counting principle. And now let's look what is different in the general case, in the case when patterns can overlap. So to understand how it works, we need first to introduce the notion of autocorrelation polynomial. And this notion will help us to count occurrences of patterns that can overlap. So let us look what it is. The autocorrelation polynomial is basically 1 plus some terms, some monomials of form zeta in some power. And we add a monomial in powers j if we can shift the permutation along the diagonal by j positions, so that the resultant permutation matches itself. So for example, for the identity permutation, if we don't shift it, it matches itself, so it's always 1, which is presented in the polynomial. So every autocorrelation polynomial starts with 1, but we can shift it by 1 position along the diagonal, and we can see that it matches itself, so we add z. We can excuse me, we can shift it by 2 positions as well, and it still matches itself, so we add z square. And we can shift by 3 positions, so we add z cube. Similarly, if we consider a permutation 1, 3, 2, 4, like this, we can see that if we shift by 1 position or by 2 positions, there is no match, so we don't add z or z square. But if we shift by 3 positions, there is a match, and so we add z cube. And to show one more example, I would like to look at the permutation 3, 4, 1, 2. And here the difference is that we need to shift along the other diagonal, namely not from the lower left to the upper right corner, but from the lower right to upper left. So here, if we shift by if we shift by 1 position, there is no match. But if we shift by 2 positions, there is a match, so we add z square. And if we shift by 3 positions, there is no match, so the resultant polynomial is 1 plus z square. So here maybe the question is how to choose the diagonal, the one or the another, the other. So the answer is we need to compare the first and the last entries of our permutation. So if
I'm sorry?
the first, yes?
Can I ask a question? Is it
Yeah, sure.
Is it obvious that it can only, so each time you shift by 1 to the right, there's only one way at most that it can match?
So if we
Oh yes,
if we
because
take,
it's a permutation.
yeah.
Okay,
So you
yes.
can see that it's either match or don't match. So
But
so
is
yeah.
it possible that sometimes when you move one to the right, sometimes you need to match it from the right corner, from the bottom left corner, and sometimes you match it from the bottom right corner?
So yeah, it's exactly what I'm going to say. So
Okay.
if we go from left to right, when we do this, when the first entry is less than the last entry, because if we shift this permutation from right to left, This mean that the lowest entry cannot match, because the lowest entry, which is here, it's always less than the last entry, and so it's not possible to move in the left direction. And so it's always like this. So if you see that the first entry is lower than the last entry, you go from bottom left to upper right. And if it's not the case, if the first entry is greater than the last entry, then you should move from lower right to upper left. And in fact, we can always do the reverse. Namely, we can rewrite the pattern from right to left and replace 3, 4, 1, 2 by 2, 1, 4, 3. And we can see that the diagonal will change, but the pattern itself and its autocorrelation, the autocorrelation polynomial of the pattern will be the same. And in fact, the number of occurrences will be the same. So in fact, if we study these patterns in terms of asymptotics or in terms of enumeration, it's sufficiently to study those of these patterns for which the first entry is less than the last. And this is what we will do a bit later. So to proceed to the result that was known, to the enumeration result, if patterns can overlap, then the idea is more or less the same, but it is done in more complicated way, because here we need to replace some entries not by pattern itself, but sometimes by clusters. So we take a permutation, and if you're familiar with the way how it's written in the symbolic method in generating functions, so we take the generating function of permutations, so it's n factorial z to the n. And then when you replace some of entries by blocks or by clusters, we replace the variable z by the corresponding generating function of cluster. So here you can see that you have a generating function of cluster in the denominator. In the numerator, we have a generating function of one cluster, and u minus 1 represents the inclusion-exclusion principle. So the idea basically is the same, but the way how it's done, it's more complicated. And here, for example, it's much more difficult to write exact formula, but it's still possible to write the generating function. And we can find, using this generating function, the asymptotics of this number of occurrences. And the result that I want to present is...
I'm sorry,
yes?
can you explain a little bit again this formula? There's something I missed. So you're summing from n goes to 0, from 0 to infinity,
Yeah.
and you've got n factorial. Why is there an n factorial here?
So here, basically, you start with permutations. So the generating function of permutation is n factorial z to the n. And now I replace z by something more maybe ridiculous. But what is the meaning of this substitution? So
Oh yeah, you say it's either a usual block, either z, you don't do anything, or else you put a big block of size. Well, it's not going to be p, but it's going to be a cluster. It's going to be a cluster of a certain size. Each block has size p, but they can overlap, and so you've got this zp divided by 1 minus your polynomial, but you say you've got your... Okay,
exactly.
Thanks.
So okay. So to asymptotics, it was known and it was the result of Bona. And in fact, it was done even early in a bit different notations and backgrounds, that the asymptotic probability to have exactly k patterns 1, 2, so the simplest possible patterns, it behaves like a Poisson distribution with the parameter 1. So it was known, and you can see that the number of occurrences, so the probability of a greater number of occurrences decreases with this number. So the greater is k, the lower is the probability, but still they are all comparable. So this value doesn't depend on n. And we will see that it's different in general case. So what we found first, in the case when there is no overlaps, we can see that if we rewrite generating function by class on, meaning that here we replace each position just by a block. So from this generating function, we can extract asymptotics. And now we can see that as long as the size of our pattern P is greater than 2, and for non-overlapping permutations, it's always the case, then the number of the probability to have exactly k very tight occurrences of this pattern depends heavily on n, and it decreases very rapidly comparing to pattern to permutations avoiding this pattern. So if k is equal to 0, meaning that permutation avoids this pattern, then this probability is 1, meaning the dominant term. And so it's this behavior is different from what we have seen for the simplest pattern. And for overlapping permutations, for overlapping patterns, it's even more complicated, meaning that there are 3 different cases depending on the behavior of the autocorrelation polynomial. So first of all, it turns out that
I'm sorry.
Yes.
In the previous slide, I was confused. So P was not. So P here was not the autocorrelation polynomial in the generating function of
So P
P
is the size of the autocorrelation
no, big
polynomial.
P, big P.
Big
in
P,
the generating.
Big P is the generating function of all permutations.
Okay.
And so here
okay.
we replace this z by a function to obtain generating function of occurrences. Is it okay?
Yes, thank you.
Okay, so comparing to this case when there are no possible overlappings of patterns, in the case when it's possible to have overlappings, there are 3 different cases. And the differences between the behavior of autocorrelation polynomial. So if we write the autocorrelation polynomial as 1 plus the lowest term, z to the n, plus some terms of higher order, it turns out that the behavior depends on m. And so if m is the largest possible, meaning if it's p minus 1, where p is the size of our pattern, then it turns out that the behavior is exactly the same as in the previous slide here. So for non-overlapping patterns and for patterns that are almost not overlapping, meaning that the overlapping is only on the last position. Well, for these 2 types of patterns, the behavior is exactly the same. On the other side, on the other pole, we have the case when m is less than p minus 2, and the behavior is is different. So here we can see that there is no coefficient, and it depends on m, on this value, like this. And in the middle, we have something like phase transition. So we can see the, some constant, but this constant, it's not very simple. It's some, it's a sum or some binomial coefficients. And that's how it works. And this is done by the approach, asymptotic approach of Borinsky. And if I have time, I will show you how it works. And maybe I will say some words why there are differences in these three situations. Now, just a few words about overlappance itself. So when we started to look at our patterns, we found that the behavior of overlappance is interesting for us too. And we found their asymptotics. That's what I'm going to talk you right now. So first of all, what kind of object we are looking for? What kind of object we are going to discuss? So we discuss exactly the permutations that overlaps when we shift them along the diagonal from left to right, like in the first two examples. And if it's so, we can see that if the permutation is overlapping, then it means that there is a block in the lower left corner, which is exactly the same as a block of the same size in the upper right corner. And you can see that if these two blocks are intersecting, then we can consider this intersection. And this intersection appears at the same time in the leftmost corner and the rightmost corner. And so we can choose a block of which size is less than the initial block, and hence we always can choose a block of size which is less than the half of size of the permutation. So these are our objects right now, self-overlapping permutations. And first, what we did, we studied their structure, and we found out that they always can be decomposed as a direct sum of blocks. So here what we can do, we take the smallest possible block, which appears at the same time in the lower left corner and in the upper right corner. And we can see that if they are exactly the same and they are lowest, then it means that they are not self-overlapping. Because if they are self-overlapping, that they have smaller blocks inside them itself, and it means that we can find a smaller blocks. So we first can extract the smallest possible block like this, which is non-self-overlapping. And when we do the same for the rest, we find the second block, the third, and so on. And so we have a decomposition into a series of non-self-overlapping permutations. So here we have some of them. Here we have the same, but in different, in the opposite order. And in the middle, we can have either a non-self-overlapping permutation or just an empty position. And so this decomposition leads to the enumeration, namely, we have an equation for the generating function of non-self-overlapping permutations. So here, what we can see, we see exactly, in fact, the structure that we discussed on the previous slide. So on the left side, we have all permutations. In the numerator, we have either empty permutation or non-self-overlapping permutation, meaning that it's exactly the middle block of this permutation, which is tau in this picture. And in the denominator, it's the sequence of non-self-overlapping permutations. And a square inside means that we have this sequence twice, so below and above the middle. So this is the reason, this is the explanation of this formula. And from this equation for generating function, we can extract asymptotics for non-self-overlapping permutation, which turn out to be like this. So most probably, and in fact, the first term, the dominant term, was known. It was found by Bono. So most probably a permutation, a random permutation, is non-self-overlapping, but we found as well the complete asymptotics. And what is interesting for me is that in this complete asymptotics, we have self-reference property, meaning that the constants count non-self-overlapping permutation as well. And in the denominator, there are foreign factorials. So this was a kind of interlude step aside. And now I would like to return to patterns. And now it will be patterns in matches. And we will see that there are many parallels. There are many parallels between patterns in permutations that we have already seen and patterns in matching. So first of all, our object, namely matchings, what it is. So we take to compose a matching of size n, we take two endpoints on the line, and we join them by n non-intersecting arcs. So we obtain something like this. And it's clear that the total number of matching is 2n minus 1, 2 factorials. And what is interesting for us, it is some special kind of patterns that we can see inside. So what kind of patterns we're interested in? So we take several starting points. For example, here we take 3 starting points that are consecutive. And we want the ending points to be consecutive as well. So both the starting points and the ending points form an interval. And so if we consider patterns like this, we call them adhered patterns because that mean and adhered, meaning that if we fix k starting points consecutively, the ending points will be consecutive as well. So these adhered patterns can be encoded by permutations, because if we take a pattern like this and we numerate the starting points from 1 to p, then the ending points will be automatically enumerated according to the arcs. And so it would be a permutation of size p. So what we're interested in? We're interested in counting them, and meaning that we count the number of occurrence of this type of patterns in matchings, and we would like to find asymptotics of that. So more or less the same idea, the same goal as we saw for patterns in permutations. So to do this, we start with some properties that will be helpful for us. So first of all, we can see that if we do some operation that we called adhere twist, then the number of patterns, of some time will be the same. So here we consider two types of operations, which are more or less the same in terms of the idea. So we take all starting points, and these starting points, these runs, are consecutive, and they are separated by ending points of some arcs. So what we do by left adhere twist, we reverse all consecutive runs of starting points. So here, for example, 11, 12 is reversed, and we obtain something like this. The same is for 1, 2, 3, 4. And as well, here is the left adhere twist, but we can do right adhere twist, meaning that we reverse all consecutive runs of ending points. So here, for example, we obtain the same, but for some
I'm sorry.
I think that Dr. Khaydar has a technical problem. You have to wait here.
Okay. I sent a message in the chat, but if he's cut off, he probably won't see it. So I don't know if it's just his connection. I think someone should contact him by email or something.
Okay, thank you.
Okay, can you hear me?
Yes, please.
Yeah, I'm sorry, the connection was lost. So
You can share
just
again your slides, please.
Yeah, so can you?
Yes,
can
it's
you?
okay. It's okay. Thank you.
Okay, yeah, so okay. So what I did, I have introduced left and right adhere twist, and in terms of patterns, it is more or less the same as we have seen for patterns in permutation when we do a reversion operation. So when we move from one diagonal to another diagonal, we can do the same here. So for example, here we can see that if we have a pattern which is encoded by the permutation 132, we can do the right inherent twist, and it's exactly the reversion. So we obtain 2, 3, 1. And in particular, what is interesting and important to us, that with this operation, we can always obtain a pattern such that the first entry is less than the second entry. And in terms of enumeration and asymptotics, we have the same. So if we have a right inherent twist or a left inherent twist, then the number of occurrences of the resulting patterns will be the same as the number of occurrences of the initial pattern. So when we start at the number of occurrences, we can always do inherent twists and continue if it's more convenient to us. Now, what I'm going to do, I'm going to show you how it works for the simplest pattern, for the pattern 2, 1. So here it's like this. In this notation, I will omit 2, 1 for simplicity, just for several slides. So first we have several recurrences. The first recurrences is how to obtain the number of permutation of size n+1 with exactly k occurrences of the pattern. So we take a permutation, a matching of size n, and we would like to construct a matching of size n+1. So we add one additional point at the left, and we need to draw an arc. And we can see that there are 2n+1 possible positions for the end, but the positions are different. So for example, if we draw an arc like this, then it means that an additional pattern appears. So we have the term like this, meaning that to obtain exactly k patterns, we need to start with k-1 patterns. Another situation is when we destroy a pattern. So it means that if we want to obtain k patterns, we need to start from k+1 patterns, and each patterns can be destroyed in two ways. We can put the end here or there, and so the number of possible choices is like this: 2k+1 being k+1. And for all other possibilities, the number of patterns, the number of occurrences is the same. And so the resulting formula like this. And this is the starting recurrence that we use to find exact numbers. But in fact, what we observed after that we can obtain numbers more easily. So first of all, we can obtain any number of occurrences, any number of matching with exactly k occurrences from the number of matchings that avoids this pattern. So the idea is to take some matching that have no patterns and to double some of its arcs. So doubling an arc create exactly one occurrences. So we add k arcs, and n choose k is the number of doubling. And now what is important to us is to obtain the number of pattern avoiding matchings. And this can be done with the inclusion-exclusion principle, just as usual. So we take all patterns, we deduce patterns with at least one occurrence, then we add all matching with at least two occurrences of patterns, and so on. And it happens that this inclusion-exclusion formula can be nicely rewrite in terms of generating functions. So if we take a generating function that count the number of occurrences, then it happens that the exact form of the derivative is like this. And here we take a derivative because in the previous slide, we can see that we need to double some edges, some arcs. And to double some arcs, we need to have at least one arc in our matching. And this means that we need to pass two derivative. And at the same time, the doubling in this formula is represented in the numerator in this exponent. And u minus 1 is a usual exclusion argument. And from this formula, we can easily find an asymptotics with the help of asymptotic methods of Lajolet, for example, or even by just some manual, something that can do by hand. And it happens that the probability distribution is Poisson, as well as for patterns in permutations, but with another parameter, it's 1/2. And this 1/2 represents, in my opinion, the fact that the number of points in matching is 2n comparing to n in permutation, roughly speaking. So it's how I imagine it for myself. So this is how it works for the simplest case. And in general case, we need to do something similar to permutation patterns. So first we define autocorrelation polynomials. And here I would like that the permutation that represent a pattern possess the property that the first entry is smaller than the last entry. So for example, 1 to 3 is good, but 3 to 1 is not. But we can do what we want by the inherent twist. It's also always possible. So what we do here, we shift right by j positions all this construction. So for example, for 1 to 3, we shift by 1. We can see that the pattern match itself. It's okay. We're at z. We shift by 2 position. It's also okay. For the permutation 2, 1, 3, meaning for the pattern that is represented by this permutation, both shifts are not good because there is no match. So here, the autocorrelation polynomial is just 1. And for 2, 1, 3, 4, we can see that it's 1 plus z squared because we can shift by 2 positions. So with this notion of autocorrelation polynomial, which is quite similar to what we have seen for permutation patterns, we can find generating functions and their asymptotics. And in the simplest case, when pattern is non-self-overlapping, we can see that generating function is a composition of the generating function of matching and this simple form z plus u minus 1 z p. And this means exactly that if we have a matching, we can replace each arc by our matching, by our pattern, or we may not replace it. So that's exactly the same idea as we have seen. And for this situation, we have an asymptotics. And the probability to obtain exactly k patterns also depends on the size. And it means that most probably for the patterns of size at least 3, the huge permutation contain no pattern at all. So if k equals to 0, then this dominant term equals to 1. If not, the dominant terms depends on n, which is in the denominator, and so the probability is very small. And the greater k, the smaller is the probability. And for asymptotics of patterns that are overlapping, we have similar behavior as for permutation patterns. So exactly the same. So we take an autocorrelation polynomial of the form like this, and we can see that depending on the smallest non-trivial order n, the behavior is either the same as for non-self-overlapping permutations, either it's something like this, or something in between for the size p minus 2. And the difference for matchings and for permutations that we have seen in the beginning is the occurrences of these powers of 2 in the denominator. So the difference is here, 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 and here. So that's all for results. And I'm not sure if I have enough time to show you proofs. Just maybe a few words.
One
is
1 minute, please.
Yes.
Okay.
Yeah.
1 minute, please. 1 minute.
1 minute. Okay.
Yes,
So
yes,
so the idea is to represent factorially divergent series in terms of their coefficients. So if you have a series which constants depends like this. So normally they are factorials. Then there are some constants that we represent as another series. And it turns out that this mapping behaves very well. It's like a differential, which works well with Leibniz rule, with the product, and with compositions. And hence, for example, for patterns and permutations, we apply this formula. We can see that we can find the composition, the coefficient generating function of compositions. It's something like this. And now we need to extract the smallest power of z near the UK. So the idea is like this. And for matchings, it's more or less the same, but the parameters are different. But the idea is the same. So that's all. Just to conclude, we studied consecutive patterns in permutation and matchings. And as well, we studied self-overlapping permutations along our way. We used such tool as the symbolic method, the Goulden-Jackson cluster method, and the Borinsky approach for finding asymptotics. And what we found asymptotics for very tight patterns and permutations, and we found enumeration and asymptotics for adherent patterns in matchings and for non-self-overlapping permutations. So thank you very much for your attention.
Thank you for you, Dr. Khaydar, for this nice talk. Please, are there some questions? Have you some applications of this pattern in biology or physics or something else?
Yeah, thank you for this question. In fact, I should have mentioned it before, but the motivation for studying this kind of patterns in matchings came from biology. So we started secondary structures in RNA. So each RNA can be represented as a line, and on this line we can see some different nodes. Like, but for us, the nature of nodes were not that important, meaning that we were interested in secondary structures, meaning that we looked at the possible relations. And so we can represent in some approximation, we can represent this RNA as a matching. And what was interesting for us was if what we could see in theory, meaning in patterns what we have discussed right now, was it the same as we could observe in real RNA? And when we have our research, it turned out that, in fact, it was very different. So, for example, as I mentioned, in theory, if we make a twist and here a twist, then the number of occurrences will be the same for different kind of patterns. For example, for patterns 1 to 3 and patterns 3 to 1, the number of occurrences will be the same. But in practice, for real RNA, these numbers are very different. And for the patterns of 3 to 1, there are a lot of occurrences, while for pattern 1 to 3, the number of occurrences is negligible. It's almost zero. So for us, it was very interesting that this model is at the same time representative and not, because to represent a real RNA, we need to add something, some weights maybe, so that to count them appropriately.
Okay. If you can go to slide 7, please. Slide 7.
Yes. Slide 7.
Yes. What means U in this formula, theorem plus on 2022? What means U here?
Oh, yeah, I can see. The problem is that I forgot to write it here. So here in this part, to the left of the sign of equality, there should be U powers K. So
Okay.
you count the number of occurrences. I'm sorry for this typo.
Okay.
And M should be K, of course.
Yes. There should be U power K.
Okay. And the second summation is over with respect to M to K. Okay, nothing. Okay.
Yeah, in the second part, it looks like it's okay.
Okay. I have another question, maybe outside. When you discuss the position of M with respect to P minus 1, P minus 2, and less than P minus 2.
Yeah.
Okay. What about if M is bigger than P minus 1, or it's not possible?
Well, it's not possible because P is the size of permutation.
Okay.
The size of the pattern, and so the autocorrelation polynomial has a degree which is less than P.
Okay. Thank you. Are there other questions, please?
Yes, I've got a question.
Yes, please. Yes, please.
Actually, I've got many questions, but
Yes, please.
Don't hear you, Christopher.
Oh, is it okay?
Okay.
Yeah, no, it's
okay. Yeah, the first question was a remark on what you just said about seeing that the patterns that you had theoretically did not match those of the RNA. So the RNA probably has a certain kind of planar structure, a little bit. I mean, it's contained in a cell, or maybe it's got a physical structure. And it seems like, I mean, when you look at these, so first of all, it's what you're going to get as a code diagram. I mean, those matchings, also called code diagrams, they're probably going to be close to those of loops in the plane. And so they're probably going to have these properties of code diagrams, which are called Gaussian. And maybe also the fact that the RNA is probably not self-intersecting that much the interlacing of the chords will also have certain properties. So for instance, the reason why maybe you see 3 to 1 much more than 1 to 3 or the opposite is maybe due to the fact that you're counting the number of intersections of the chords. And maybe that's a good way to measure the weight, for instance. I don't know. I'm just kind of, it's just an idea. The second thing I wanted to mention is about, it seemed like in your second part of the talk about, so have you heard about the split decomposition or the Cunningham decomposition of a graph? It's a way to, yeah, so you can make this interlaced graph where the nodes correspond to the chords and the edges of the graph correspond to when two chords intersect. And then you can try to reconstruct your chord diagram, not uniquely in terms of this graph. And then lots of these enumeration can be done using this graph to make some generating functions, having as you do for permutations. And my last comment before I ask my question, my last comment is that so maybe it's, when you've got these patterns for chord diagrams, you can be overlapping on the right or on the left, but you can also be overlapping yourself inside and outside, can't you?
So you mean I think this one?
Yeah, so
like
you can be overlapping. So you can be overlapping if you go a little bit to the right, a little bit to the left, but you can also move them both inside. And that's also overlapping.
Yes.
Or outside. Yes.
But,
so now there are four ways you can overlap.
Right? Yeah, but all these possibilities are encoded by this diagram, meaning that if you can overlap inside outside, you cannot overlap right or left, and we should do right or left and here twist to pass from one way of overlapping to another. So either we can do it right left, or we can do it inside outside.
Okay, but there are still two possibilities once you've, okay. I mean, maybe at most.
Well, it depends on what you want to do. So yeah. If I prefer to fix the first entries of my permutation to be less than the last entries, and so in this case, what I can do, I can pass from left to right, not from inside to outside.
Okay. Okay, and so my question was about the slide you were just on previously.
This one?
No. Before that, the one before where you had the asymptotics. It seems very curious. The ones with the asymptotics. It seems. Do you have an intuition for the various behaviors of the asymptotics in terms of the overlapping? The one the slide which is, I think it was 17. It was mentioned by someone.
17? No.
Or was it 7? No, not 17.
Do you mean asymptotics of overlapping permutations or patterns?
Yes.
So maybe one.
Okay, let's say patterns.
Okay, for patterns, you mean this one maybe?
Yes.
Or that one?
The one before.
This one. Okay.
No, the other one. The one where there are the three cases.
Okay, this one.
Yes. Do you have an intuition for these three cases? Yes.
In fact, yeah, that's a good question why it happens and how to explain it. Right now, frankly speaking, I have no idea.
It seems. I'm sure. So it's not. This is not going to give us some intuition, but some way to visualize this would be if you take a very big random permutation and you start putting all the squares where you can see where you can find your pattern, and you look. So it seems like there's a kind of a critical phenomena. I mean, it's kind of a critical parameter where you're changing. I mean, this power m. It's there's a kind of change of phase where they can cluster a lot, and then you're going to see much more. And if they cannot cluster a lot, they have to move to be very sparse. But it seems like, I mean, it seems like just changing one m going from p-1 to p-2. I mean, it shouldn't change anything if p is very large, right?
Yeah.
Or mind you, maybe the two formula give about the same thing when p is very large. But
yeah, I agree. So for me, it's not very clear
for p-1 and p-2. If p is very large, maybe they're actually almost the same thing.
Yeah, so it's not about the size of the pattern. It's about the way how it self-intersect, how it can overlap. So it's more about that.
I mean, okay, look at the.
Sorry.
Not depend on p.
Okay.
Yeah, that's true.
And what I find weird is that if p is super large, so your pattern is super large compared to n. For me, these two formulas should start getting to be the same, right? Because whether m is p-1 or p-2, not much difference.
Well, we cannot. I'm not sure it's possible to do p very large comparing to n, because here we fix p and
say log n. Say log n.
Well, yeah, I'm not sure that it will work exactly like this in this formula, because the behavior, if p depends on n, the behavior really made different. Maybe different.
I see, I understand. Okay.
Mm-hmm. So yeah. Your question is really
p
interesting.
Is fixed.
How how it will behave if we will allow p be dependent on n. But in this situation, it's not the case, because p is fixed and it is n which is growing.
Okay. I've actually got one last question, but maybe you can just send the slides and I can ask them privately. I don't want to be taking too much.
Yes, please, Dr. Khaydar, can you send me after the talk your slides to put them online?
Yeah, sure,
okay.
Sure.
Thank you. Other questions, please? So, if no questions, we have to thank again Dr. Khaydar for this nice talk. And see you next Tuesday with our next speaker, Tatiana Starikovskaya from Ecole Normale Supérieure Paris. And she will continue with pattern matching. So thank you again to all, and see you next week. Thank you, Khaydar.
Thank you very much.
Thank you.
Thank you. Thank you for attention.
And please don't forget to send me the slides, please.
Sure.
Thank you.